네, 그래서 오늘 참석해주신 모든 분들께 감사드립니다. 오늘은 2025 이온큐 서머 리서치 멘토링 프로그램 행사의 마지막이 되겠고요. 각자 이제 지난 거의 한 달 반 동안 이온큐 리서치, 이온큐 연구자분들과 이제 좋은 멘토링 프로그램을 진행을 하셔서 그 멘토링 프로그램의 결과를 이제, 이제 여기서 발표하는 그런 시간이 되도록 하겠습니다. 첫 번째 순서는 그 큐비쿼터스 팀에서 발표가 있겠고요. 공석현 님이 발표를 해주시도록 하겠습니다. 이 팀은 Solving Constraint Satisfaction Problem with Variational Quantum Algorithm on Disk Devices라는 주제로 발표를 할 것이고요. 이 팀의 멘토는 데니달 박사님이십니다. 발표 자료 있으시면 공유 부탁드리겠습니다. 네, 잘 보입니다.
네, 들리시죠?
네, 진행해 주시면
영어, 네,
되겠습니다.
영어로 하겠습니다.
예.
Hello, this is Team Qubiquitous. Today I'm going to present our work on solving constraint satisfaction problems using a variational quantum algorithm, specifically QAOA. Our team was advised by Dr. Danny Dahl, and I'm the speaker, Seokhyun Lucas Kong, a final year electrical engineering undergraduate student at Sungkyunkwan University. We addressed two problems in our research, the four corners map coloring problem and the instant insanity problem, which took 3 and 4 weeks respectively. The four corners map coloring problem is to assign one of two colors to each of the four states in the four corners region, such that neighboring states, those that share a border, have different colors. The twos on the left are the answers, and while the twos on the right are not the answers. In the following section, we introduce two encoding schemes, unary and binary. In unary, also called one-hot encoding, each state I is represented by two variables alpha and corresponding to two possible color choices for the region. Here, red and green. The possible solutions are shown below. The variable xi alpha indicates whether each region I is assigned color alpha, 1 if assigned and 0 otherwise. With that, we can derive two constraints. For constraint 1, each state must be assigned exactly one color. And for constraint 2, neighboring states must be assigned different colors. Therefore, we can set QBO as the sum of these two constraints. However, to reduce the size of QBO and consequently the Hamiltonian, we can satisfy the first constraint C underscore O by preparing the initial state with Bell states. With this construction, the QBO reduces to the remaining constraints C underscore NN. In binary encoding, each state I is represented by a single variable xi, 1 if red and 0 if blue, since each state can take only one of two colors. The two possible solutions are shown below. Binary encoding requires only 4 qubits, half the number needed in unary encoding. Accordingly, the first constraint CO, ensuring one color per state, is automatically satisfied. The only remaining constraint, CNN, which requires that neighboring states be assigned different colors. Different from the variables xi in 0 and 1 used in the Kubo formulation, quantum Hamiltonians are usually expressed in terms of spin variables zi in -1 and 1, which corresponds to the eigenvalues of the Pauli Z operators. We map xi equals to 1 minus zi over 2 and substitute this into Kubo expression to rewrite the cost function in terms of zi as an Ising model. However, the first term H unary can be eliminated by preparing the stale with Bell states for each region, which allow us to simplify H unary as follows. In the same manner, we can also represent H binary as follows. So these are the two Hamiltonian representation with two encoding schemes. As we prepared psi 0 as an initial state, we implemented a special mixer that preserved the Bell state subspace 0, 1, and 1, 0. Here, psi 0 is a tensor product of Bell states. In this way, the constraint is preserved. 0, 1, and 1, 0 rotate, or so-called mix, by beta through the mixer. The quantum circuit is parameterized by gamma I and beta I at each layer I. This procedure can be interpreted as a discretized version of adiabatic evolution, where the system evolves from the simple Hamiltonian to the problem Hamiltonian, with the parameters varying linearly and slowly. Linear ramping here mimics the adiabatic path. To clarify, we begin with the ground state HM, which can be easily prepared as a uniform superposition across all basis states. In contrast, the ground state of HC encoded the valid solution of, for example, 1001 or 0110, but it cannot directly accessible. So here, by linearly interpolating HS equals to 1 minus S and HM here is simple Hamiltonian, and S plus SHC, HC is a problem Hamiltonian. Then we can adiabatically transform the system from the simple distribution of HM to the solution space of HC. As mentioned previously, the quantum circuit with unary encoding starts with the prepared state psi 0 defined as the tensor product of four superpositions of Bell state 0, 1, and 1, 0 between 8 qubits in order to ensure a first constraints from the beginning to reduce the size of Hamiltonian. This initialization reduces the complexity of Hamiltonian. The quantum circuit is then parameterized by symbolic parameters gamma I, beta I for each layer of the cost function and XY mixture resulting in a total 10 layers. Different from the unary encoding, the quantum circuit with binary encoding starts with four superpositions of plus states to ensure full superposition across four qubits. Since binary encoding requires only half as many qubits as unary encoding, the circuit uses a total of 5 layers, each consisting of a cost function and a mixer. Here, we employ a standard QAOA X mixer. QAOA is a hybrid quantum classical algorithm. For the quantum part, the estimator, here we used a backend estimator version 2 with IonQ backend. This evaluates the expectation value HC of the cost Hamiltonian for the given set of parameters gamma I and beta I. The classical part, the optimizer, here is scipy.optimize.minimize with the cobila method. This updates the parameters by searching the parameter space to minimize this cost function. We observe that the cost decreases as the iterations progress, and we obtain the optimized circuit by assigning the optimizer's output to the circuit parameters. Figure 4 presents the sampling results with 1024 shots. The quantum circuits in both encoding scheme perform well, yielding the correct results to the problem. Utah and New Mexico are assigned the same color, and Colorado and Arizona are assigned the same color. So to wrap up, this is the final poster for the four corners map coloring problem, and we would be happy to share with Q Center if needed. Let's dive into the second problem, the instant insanity problem. Given the set of blocks, each with different configurations, the goal of instant insanity is to stack four cubes so that each color appears exactly once on each of the four sides of a tower. Each cube is represented by three edges, each corresponding to the pair of opposite faces. For each edge, two possible directions, top, bottom, and front and back, are regarded as a distinct case. Each qubit represents the state of cube. Each cube has six possible states, as shown in figure 3, depending on which pair of faces are assigned to top, bottom, and front, back. The first cube requires only three qubits since the distinction between the top, bottom, and front, back is relative for the first cube. Therefore, a total 21 cubes are needed. However, as we tried, the graph encoding with 21 qubits attempts to solve the problem by incorporating both the top, bottom, and front, back configuration into one cost function. However, due to its complexity, this approach took over an hour to run and produce the results with low accuracy. We suggest a divide and conquer approach with an alternative scheme that considers only a single pair of rows or faces, either top, bottom, or front and back. It doesn't matter. It This approach allows us to narrow down the candidate solution and select one with a zero cost. We then run the next trial to get new candidates for the remaining pair of rows using an updated cost function that incorporates the first solution through post-processing. Finally, we combine the solutions, ensuring that no contradictions arises between them. To satisfy the condition that each color appears exactly once each rows, every vertex, here color, must have degree of 2 or appear twice, which implies that a cycle must be formed in the combined graph of all colors. Figure A to C show possible candidates for one pair of rows. In the classical divide and conquer approach, each qubit represents a configuration of a pair of opposite faces, corresponding to one edge of the cube in figure 2. Therefore, each cube can be one of three possible states and a total of 12 qubits needed. In this approach, we have two constraints here. Constraint 1, each cube should occupy exactly one state, so-called one hot per cube. For constraint 2, from the graph, every color should appear exactly twice within one pair of rows. Accordingly, we can set the cubo as the sum of these two constraints. However, to reduce the size of cubo and consequently the Hamiltonian, we can satisfy the first constraint C cube by preparing the initial state as a tensor product of Dicke state for each cube. As we prepare the tensor product of Dicke state as an initial state, we implement a special mixer that preserves the Dicke subspace 001, 010, 100. In this way, the constraints are preserved, rotate, or mixed by beta through the mixer. Along with the Ising models, we employ a QAOA ansatz, estimator, and optimizer in the same manner as the four corners map coloring problem. These are the top 5 candidates for the first pair of rows, and we select a zero cost solution. This solution corresponds to the graph shown on the right. Based on the result of the first iteration for one pair of rows, we suggest two approaches for post-processing. Here, modifying the Hamiltonian in the next iteration for the remaining pair. For approach 1, we add the bias term of the first zero-cost solution. We added an additional penalty strength to the bias and increased the circuit depth from 10 to 15. For the approach 2, delete the solution variables, um, W3, Z2, Y1, X2 from the previous C graph, our cost function, since S should not be reused. These are the top 5 candidates from the result after second iteration with post-processing applied. Again, we select the zero cost solution, which corresponds to the graph on the right. For the final check with the solution A and the second solution, C, we verified that no edges are shared. Therefore, the correct solution for the whole cube, um, top, bottom, and front back, is obtained, which corresponds to D. Note that there is no corresponding zero cost solution for B. So the B can be the partial solution, but it cannot be the final solution because there is no corresponding solution. This is the final poster for the insanity problem, and we would be happy to share if with Q Center if needed. We're glad to have solved the hackathon problem, which feels like something left behind. So we sincerely appreciate the guidance of our advisor, Dr. Denny. Thank you, and any questions are welcome. This was 석현 Lucas Kong.
Okay, thank you for a nice talk. Any, I think, any questions from the audience? If not, I think we can move on to the next speaker. So thank you again for a nice presentation, Team Qubiquitous and the Sakyan. Next speaker is from QuantuMMania team. There's one more M, but I don't know how to pronounce it. So I would say just QuantuMMania.
You can just pronounce it as QuantuMMania.
Okay, sounds good. So why don't you share your screen and share your presentation? Okay, I can see your slides, so you can start.
Okay. So, hello everyone. Good morning, evening, everyone. My name is Justin Kim, and I am with the team QuantuMMania. And in our team, we have Chanho Won, Yeonsu Park, and Sunghoon Kim with me, and our mentor was Dr. Denny Dahl. And today, I am very excited to present our research for the mentoring program, titled "Improving the Performance of QAOA Using Parity Synthesis Network." Okay, today, we'll begin with a brief introduction of the QAOA algorithm. We'll then discuss a major bottleneck that limits its performance on current quantum hardware. After that, we'll introduce the parity synthesis network as a powerful solution to this bottleneck. And we'll then walk you through our experiment setup and the results, where we compare the parity synthesis network with a naive QAOA method. And finally, we'll conclude with our key findings. So, what is QAOA? The quantum approximate optimization algorithm is a hybrid quantum classical algorithm, and it's one of the most promising candidates for solving complex combinatorial optimization problem on near-term quantum computers. So the process starts by taking a classical cost function for a optimization problem and mapping that cost function into a Ising Hamiltonian. This Hamiltonian represents our cost function h c of gamma, and the QAOA circuit then works by repeatedly applying the cost Hamiltonian along with a second operator called the mixer Hamiltonian, which is the HM of beta, to guide towards the optimal solution. So this table shows a very high level stages of QAOA. First, we start off with the function we want to minimize. In this example, it's given as a QO, which is an unconstrained problem with up to quadratic terms. Next, we substitute the xi's with 1 minus si over 2 to convert the binary variables of values of 0 and 1 to spin variables of values of -1 and 1. This allows us to directly replace the spin variables with the poly z operators, the third one. And finally, we just alternate the hc of gamma and hm of beta to make the ansatz for the QAOA. The key takeaway here is how these mathematical operators are translated into actual quantum gates. Single qubit terms in the Hamiltonian becomes just a simple rotation gate, but the two qubit interaction terms require the use of CNOT gates. And since two qubit gates have significantly lower fidelity, reducing the number of two qubit gates like the CNOT gate is one of the most important goals in improving the performance of any quantum algorithm. So this brings us to the main bottleneck of QAOA. The circuit for the closed Hamiltonian is almost always the most complex and resource-intensive part of the algorithm, and it is also the usually the primary consumer of the two qubit CNOT gates. And these gates are the main source of inefficiency and error on today's quantum hardware. Therefore, any method that can reduce the number of CNOTs in this part of the algorithm is very important and valuable. So the standard or naive approach to building the circuit for the closed Hamiltonian is to just tackle each term in the Hamiltonian at a time by using a structure called the phase gadget. A phase gadget is constructed in 3 stages. First, it uses a ladder of CNOT gates to entangle the necessary qubits, and then it applies appropriate RZ gates. And then lastly, it uses another ladder of CNOTs to disentangle everything back to the standard basis, the computational basis. As you can see, this is an example of a simple 4-qubit Hamiltonian with the Hamiltonian, and this process is repeated for every single term in the Hamiltonian. This method is very simple and straightforward, but as you can see, it's very inefficient because it performs a lot of redundant works. And because it has, a lot of repeated works, the CNOT count of this method grows very quickly as the formula shown below the slide, at the bottom of the slide. Okay, so how can we overcome this bottleneck? The solution is to use a more holistic approach called parity synthesis network. This method was introduced in a paper co-written by our mentor, Dr. Dahl. In this method, instead of building the circuit term by term, this method analyzes all the terms in the entire Hamiltonian at once and build a highly efficient CNOT network. Essentially, what we want to do is we want to perform the entanglement building stage only once and do the unbuilding stage or the return journey as described in the paper only once at the very end of the network, avoiding all the repeated and redundant work in the middle that can be found in the naive phase gadget method. So the algorithm we implemented based on the paper uses a greedy heuristic. In each step, the heuristic greedily chooses the closest target parity. So that's the term with the smallest Hamming weight from the current one. And after that, it adds a single CNOT gate to make progress towards that target parity. And it applies the appropriate rotation gate at the exact moment once the parity is completed. This loop continues until all the terms are handled, and then a final sequence of CNOTs are applied to disentangle the circuit back to the standard basis. So this circuit diagram at the bottom shows the circuit for the same Hamiltonian we showed earlier. And as you can see, that is much more compact than the one compared than the circuit for the naive phase gadget. And this example is done for a very short and simple Hamiltonian, but imagine how much advantage we can achieve if we do this for much more complex Hamiltonians with many qubits. So where does this advantage come from? It's all in the overlap of the CNOTs in the circuit for the cost Hamiltonian. For simple quadratic terms, the naive method is already optimal, only requiring two CNOT gates, one to build the entanglement and another to disentangle. So there isn't any room for improvement here. However, for problems with high order terms, cubic, quadric, and beyond, the naive method performs a huge amount of redundant work. This is where the parity synthesis network method shines by identifying the shared structure between the complex terms and doing the building stage only once and doing the unbuilding stage also only once. Okay, so to test this, we needed an optimization problem that naturally has a lot of high order terms. So we decided to go with the K-set problem. So a K-set problem is a very classic NP-complete problem in computer science. The goal of this problem is to find an assignment of true or false, so either 0 or 1, to a set of variables that satisfy a list of logical clauses, Boolean clauses. This is just a simple example of a 5-step problem with 8 variables from x0 to x7. And each literal in a clause is connected with the or operator, and the clauses are linked with the and operators. Because K-set problems usually have many solutions, we specifically constructed a problem with only one unique correct answer. This allows us to clearly verify that the QAOA algorithm successfully found the right answer. If we were to just use any K-set problems with many solutions, we won't know if the algorithm approximated correctly to the correct answer, because approximating to basically anything would be considered as correct, and we don't want that to measure the performance of the algorithm. So first off, we began with 4 qubits reset problem with a unique solution of 0, 1, 1, 0. This is the full problem statement is shown in the slide, and below that is the Ising Hamiltonian corresponding to this problem. As you can see, there are 4 cubic terms, and this is a perfect Hamiltonian to test out the advantage of parity synthesis network. So we used a QAOA ansatz with 10 layers and used the Qubiquitous optimizer to optimize the parameters. The CNOT count for the ansatz built with our parity synthesis network was 90, while the naive phase gadget method required 140 CNOT gates, which is a pretty big difference even at only 4 qubits. So these plots shows the optimization process on a noiseless AR simulator. Both methods successfully converged to the ground state energy. And this is the plot of the histogram of the counts of the measured outcome. The both parity synthesis network and naive phase gadget approximated to the correct answer, which is 0, 1, 1, 0. But one interesting thing is that the parity synthesis network, because it has a shallower circuit, concentrated over 1,017 shots out of 1,024 shots to the correct answer, while the naive phase gadget method only had 800 shots to the correct answer, and for the same 1,000 and out of the same 1,024 shots. Next, we did a simulation on a noisy simulator with 2% depolarizing error to the CNOT gate. And as you can see, the parity synthesis network converged well, and naive phase gadgets somewhat converged, so it isn't that pretty. And if you take a look at the histogram of the shots of the measured outcome, you can see that both the parity synthesis network and the naive phase gadget approximated to the correct answer. But again, in the noisy environment, just like as in the noiseless environment, the parity synthesis network got much more shots for the correct answer compared to the naive phase guided. Next, we repeated the same experiment for a 5-qubit problem. So we've just added one more clause at the front with 4 literals to make another Boolean satisfiability problem with only one unique solution. In this case, it's 0, 1, 1, 0, 0. For this problem, the Ising Hamiltonian has much more terms compared to the previous one with up to quartic terms, which is great to test out the advantage of parity network. For the answers of the QAOA of this problem, we first tried with 10 layers just as before, but because of the deep circuit depth, the optimizer failed to converge in the optimization step in noisy environment. So we just decided to go with 5 layers of closed Hamiltonian and mixed Hamiltonian. The CNOT gate count for this problem was 100 for the parity network and 150 for the naive phase gadget. So again, there's a big advantage in the number of CNOT gates. We first ran the algorithm on noiseless environment just like before, and both the parity network and naive method converged well. And here we see the final measurement outcome of the noiseless simulation. As you can see, they both approximated to the correct answer. And just one thing to note here is that the Qiskit uses little endian district notation. So the histogram with the 00110 is actually corresponds to 01100 for the districts we actually use. So this is indeed the correct answer. But if you look at the distribution of the states, you can see there's a big clear difference in the performance. The histogram for the parity network shows that the correct state has a significantly higher count, while the naive version has only 600 out of 1,000, about 1,000 total shots. Next, we ran the simulation in the same noisy environment as before, and we can see that the parity network converged while the naive method didn't really converge before the Qubiquitous optimizer terminated the optimization process according to its own internal termination condition. And here we see the histogram of the measurement outcome for both of the methods. Only the parity network got the correct answer while the naive one didn't get the correct answer. It was actually, for the naive one, it was actually pretty much equal probability for over all the possible states, which doesn't really mean anything meaningful. So next, we try to do the same for 6-qubit, but when we did that in noisy environment, even the parity network didn't converge for 6 qubits. So we just decided to stop with 5 qubits and decided to test on much more qubit that was simulatable on the computers we had. So we tested on 10 qubits. Although there was about 30 to 40% less CNOT gates in the answers made with parity network compared to the one made with naive phase scheduled for 4 and 5 qubits is well, although it's not that significant. So we created a 10-step problem with many solutions because we decided to just compare the CNOT gate count and the optimization time, and we're not really interested whether the algorithm actually approximates to the correct answer. So the results here are much more dramatic than the ones with just 4 or 5 qubits. The parity network required just under 5,000 CNOTs, while the naive method required nearly 33,000, so almost 6.5 times difference, and that's a lot. And this also led to a significant real-world advantage in optimization time, which was more than halved for the parity network compared to the naive method. Okay, so in conclusion, our work has verified that the parity synthesis network is a highly efficient method for not only reducing the number of CNOT gates in the QAOA circuit, but also the optimization time of the answers and the reliability of the measurement outcome of the optimized circuit. And this advantage grows significantly as the problem size increases. Because the parity network creates shallow circuits with fewer 2-qubit gates, its performance is much better both in noiseless and critically the noisy environment. However, it's important to note that this advantage is only present for high-order optimization problems. But while we were deciding which problems to test on the for the QAOA algorithm, it turned out that there wasn't really many real-world optimization problem that had a lot of high-order terms. Most real-world optimization problems like the portfolio optimization and stuff can be reduced down to a qubit. So that's one thing to note here. So this work was an implementation and analysis of a method introduced in the paper called Enhancing Quantum Optimization with Parity Synthesis Network by Campbell and Mento Dahl. And the full source code for our project is available in my GitHub repository. And thank you for listening, and I'm happy to answer any questions if there's any.
I have a question. This is Philip Farah from IonQ. First, congratulations. I really liked both presentations. Very nicely done. And
Thank you.
like the way you presented it as well, not only the results. I have a question from a non-technical audience, myself. Uh, Given that in noiseless environments, I assume the gates have perfect fidelity, why are you still seeing a difference in noiseless environments? For example, in the example what you had six qubits, and there was a result, I think the 211 result, which was an erroneous one. Still,
Yeah,
it showed up.
yeah, that's also one of the interesting findings we found during our project. I assume it's probably because of the circuit test. I'm actually not really sure why there's a difference in the result of in the for the noises environments, because theoretically there shouldn't be any difference because they both have the exact same unitary operation, and also there isn't any accumulated gate errors. So that part we kind of found it interesting, and I'm not so sure about that.
And any other Danny or someone else, any other suggestions?
Could have been luck.
Could have been luck. Okay.
Yeah, but we ran the algorithm quite a few times, but all of the results showed the same results. So I think there must be something, with something to do with the probabilities of getting the outcome for the each gate, even in noiseless simulation. I'm not so sure about that. Maybe it's because just the nature of the noiseless simulation itself.
Yeah, it might be not as noiseless, but thank you. Thank you very much.
Yeah, thank you.
Yeah. So if there's no more questions, I can wait for 3 seconds. Then let's move on to the next speaker. Thank you. Thanks for nice talk. And
Thank
yeah.
you. How do I stop? Okay.
So the next team is actually, yeah. Who was next team? I somehow close. Yeah, here we go. So SeeQI research group side. Are you ready for the presentation?
Yeah, we are ready. I hope you
Yes,
can hear me properly, right?
I can hear you.
Okay. Let me share my screen.
Mm.
Second.
Yeah. I can see your screen, but it is not in presentation mode.
Oh, yeah, just Yeah, okay, so now you
Yes.
can see the screen, right? So good morning, everyone. So my name is Syed Mohammad Awzar Rizvi. I'm representing the SeeQI research group here. And our group was actually mentored by Dr. Nitter, Oliver Nitter. And the topic that we were working on was the explainability in the quantum machine learning domain. Specifically, like we wanted to understand like how the quantum circuits they are working and how they affect the learnability in QML. So our motivation was that, for example, in classical machine learning, we have tools like saliency map or feature attribution that can tell us like how the model is working. But in quantum machine learning, it's mostly still like a black box that users don't know how the model itself is working, how the quantum circuits are behaving, and how they're affecting the interpretability or the explainability of the quantum machine learning circuits. So we wanted to learn like how the quantum circuit affects and what type of functions. So functions, I will be explaining in a little bit, like functions are the mathematical models that can be fit in the quantum circuit. How can we fit different models onto a quantum circuit and how the different gates and the encoding strategy affects these learnability and how like the noise would affect that quantum circuit learning. So this is something that we wanted to explore from the very beginning, and this is something that we worked on. So the main objective in our and the results would also be relating to that was that we wanted to understand like how the encoding strategies influence the explainability of the quantum circuit models, how the data reloading, for example, would help the learnability or the explainability of the model. Again, and the choices of the circuits, like what type of encoding strategies would be more helpful and which would not be more helpful, which are more robust and which are not robust. So this is something we also explore again. And furthermore, like we also explored the problem of like the vanishing gradient. Like if you have a very long and depth circuit with a lot of qubits, you cannot learn the bigger function. So this is something we also explored. And combined all of this, we made a result that how the overall the quantum circuits can learn the model and the functions which can be uploaded or learned in a quantum machine learning model. So the basis of our work was actually based on a Maria Schwartz paper, which was the effect of data encoding on the expressive power of variational quantum machine learning models. So basically, the paper tells us that the quantum circuits actually they work like a Fourier series. When you put data into a quantum circuit, the model can output the function, which can be expressed as a sum of sines and cosines. And the coding strategy actually determines like what type of frequencies or the functions you can fit. So this is very important. So most of the quantum circuit can be actually broken down into two parts. Like for the first part would be the encoding circuit, the second part would be the variational circuit. So in this circuit, the most important thing is the encoding strategy, like what type of encoding you are using and how much frequently you are re-uploading the data. So this is very important. But second of all, there is another part, which is the variational part, which learns the input data. So we also experimented like, okay, what type of variational model or what is the effect of variational model in the overall learning. So the paper actually tells us that encoding gates actually inject the input features and the trainable gates, they affect the model coefficients. So here the coefficients mean any function, any sine cosine function that we are adding to the model. So it has a coefficient like as in the Fourier series. So the trainable gates or the variational part would affect the coefficients of the model, and how much frequencies the model can learn is actually affected by the encoding strategy. So in the first experiment, we actually experimented a little bit with the encoding blocks. So we used the three encoding gates side by side. Like for example, first we encoded the data with the R X rotation gate, then with the R Y rotation gate, and then with the R T rotation gate. And the measurement was performed in the Z basis or the computational basis. So as you can see from the results, it's a very simple 1D Fourier circuit, which can model the 1D Fourier series. So in the first figure, you can see that the model actually, when you are using the RX gate, the model actually learns perfectly and fits the model. So the blue line is actually what the model learned, and the dotted one is the actual function, the initial function. So the model learns perfectly when you're encoding with the RX gate. same goes for the RY gate. So the RY gate, if you maybe give it more epochs, then it would learn the function efficiently. But for the RZ gate, as you can see, it doesn't fit the sine curve very well. So this is something odd that we saw. And we maybe concluded that because the RZ gate commutes with the measurement, because the measurement was also in the Z-axis, so it's weak and ineffective in relatively weak and ineffective in encoding the actual sinusoidal that we were trying to encode. But the Rx and the Ry were actually better in performing when in encoding the Fourier function when we were encoding the QML circuits. So this actually helps us you to understand like what type of encoding gates which would be more preferable when you are encoding any function into a quantum machine learning circuit. And most likely the Rx and the Ry gate would be more efficient as compared to the RC when you are working with the simple Fourier's 1D Fourier transformation. So another thing is that you can actually encode the circuit in two ways. Like you can actually serially upload the data, and I will be showing the circuit in a little bit. So either you can sequentially upload or you can parallelly encode the data in the quantum circuits. So for example, and this can actually help us to see like the spectral bias or what type of encoding is actually more effective in the circuits. So we actually made a target function, as you can see on the screen. F of x equals to 0.2 plus sine of x plus sine 2x plus sine 3x. So as you can see, there are three frequency components in this function, and we will see that what type of encoding is affecting the output of the target frequencies. And the rotation gate we were used for the simple rotation gate, the Rx gate was used for embedding, and C0 gate was used for entanglement. And the layers were like sequentially, it was like 1 to 5 layers, and the qubits, number of qubits, the maximum number of qubits that we used for, again, maximum was the 1 to 5. So this is the first experiment. As you can see here, it's only the sequential circuit. In the sequential circuit, there's only one qubit. So the RY gate here is the encoding gate, and the RZ, RY, and the RX, so three gates after that are the variational circuit. So these circuits done, and the first one is actually to encode the data, and we have repeated it 3 times. So as you can see from the graph, that the model fits the actual sinusoidal very perfectly, and we have all the four all the frequency component that were initially present in the circuit, and it doesn't happen that model does not fit or does not learn some of the frequency components. So what happens if we change the circuit a little bit? So for example, we reduce in this case we reduce the variational circuit to just RZ and encoded the and repeated the circuit 3 times. So the circuit was able to learn and fit the input function with only one rotational gate with a simple variational layer. As you can see on the right side, it has all the frequency component, but it could not fit the actual sinusoidal because the variational part of the circuit was very limited. So what happens if we move towards the parallel leaf learning? Like for example, if we increase the number of qubits and make the circuit a bit smaller. So what happens is that in this case, as you can see, we have the RY rotation as the encoding gate, and RZ, RY, and RX as the rotational gate with some entangling part as well, which is repeated 2 times here. So there are 2 layers. So as you can see, this circuit learns and fits the sinusoidal wave perfectly and has all the frequency components. So this model actually works very well as well. But what happens if we, in the experiment B, what happens if we again reduce the complexity of the variational part? So as you can see, the variational part here, it also does not fit the frequency and also the actual sinusoidal frequency, the wave that we were trying to fit. But furthermore, it does not learn the frequencies present in the circuit as well. So what we concluded that even when we use a very complex answer at both the parallel and the sequential, when we use a complex answer, the parallel and sequential strategies can represent all frequencies and can fit all the frequency models. But under restricted circuits, only the sequential reuploading actually recovers the full spectrum, and it avoids the spectral bias. So in this figure, you can see the heat map of 2 different functions that we tried to fit. So here the red actually shows the heat map shows the loss function when fitting the curve. And as you can see, the x-axis shows the depth and the y-axis shows the number of qubits. And you can see if you increase the number of layers, it does not improve the overall loss function. But if you increase the number of qubits, it does not improve the loss function. But if you increase the layers and the depth, then it actually helps in learning, or it helps in the trainability of the circuit. So here the takeout is that even a single qubit with 3 or more layers can fit the target as well. But on the other hand, simply adding more qubits at a shallow depth does not help as much. So here we conclude that the real driver or the real encoding thing is the sequential uploading, while the parallel uploading doesn't help very much. It only aids the circuit learning. So second part of the problem in the circuits, in the quantum circuits in machine learning is that, okay, if you can increase the size of for example, sequentially increase the size of the circuit, but you can face like the problem of the barren plateaus. Like, okay, like if the circuit cannot learn, then there is no need or there is no use of increasing the length of the circuit sequentially. So barren plateaus, like as we all know, maybe some of you have heard. So barren plateaus hinders the training by causing the vanishing gradient problem. So it's similar to the problem in classical machine learning, where the gradients they vanish as the depth of the neural network increase. So similar can happen in a quantum circuit as well. And the local cost function mitigate, they can perform better as compared to global cost function in ideal setting, and we would see that results as well in a little bit. So actually, we wanted to test the robustness of the local versus the global cost under the realistic noise environment, and see how the answers in the circuit they are affecting the gradients. So this is a simple experiment that we ran. So here we added the depolarizing noise, as you can see, for the single qubit and 2 qubit, with some thermal relaxation and readout error. And this was actually implemented on the IBM model. So there's one thing that we tried to implement things on the IonQ simulator, but I think so it was it had a learning curve for us, and some of the actual hardware was sometimes not available. So we actually implemented this on the IBM hardware for now. So in the graphs, you can see, as in the first graph, the global cost, for example, the top one, you can see that if the number of qubits, for example, in the blue line, the number of qubits is 2. And if you increase the depth of the circuit, keeping the number of qubits small, like 2, the variance is actually, it does not decrease. So variance, so if you have good variance, the variance is not very small, then the problem of barren plateau is actually solvable, or they are not very much barren plateaus if the variance is not that small. So in the case of n is equals to 2 qubits, the variance does not decrease. So we can actually increase the depth of the circuit, and the gradient vanishing problem would not be present as much. But if you increase the number of qubits and increase the depth as well, then you can see the variance would reduce, and you would have that problem of the vanishing gradient. And in the bottom part as well, in the bottom graph as well, as you can see, we added the noise. So the first part was the noiseless part. The second part shows the noisy part. So if you add the noise as well, then you can see that increasing the depth also decreases the variance. And again, this would cause the problem of barren plateaus. But in general, if you have a small number of qubits, you can increase the depth and encode more type of sinusoidal waves as compared to parallel uploading. So you can link this part with the previous part, that sequential uploading is again more effective and more feasible as compared to the parallel upload. So this is again a summary of the previous result as well. Here the x-axis shows the depth of the circuit, and the y-axis shows the number of qubits. And you can see that the more the red part, the less the more the variance, and the less is the problem of vanishing gradient. So the more we go towards the yellow, the more you will have the problem of the vanishing gradient. So as you can see that if we increase the depth of the circuit and increase the number of qubits, you will have that problem of the vanishing gradient. So the ideal solution would be to keep the number of qubits less and increase the depth of the circuit when encoding any problem into a quantum machine learning circuit. So I would just summarize again all of the point. So we have seen that encoding govern explainability. Sequential uploading is more effective as compared to parallel uploading. The axis choice, it also matters. The Rx and the RY gate provide more sinusoidal independence. So you can actually fit the sinusoidal curve more effectively when using these gate as compared to the RZ gate. So, and the spectral bias analysis shows the sequential uploading avoids the bias and converges with fewer qubits. Furthermore, noise accelerates the Barron plateaus, which destroys the robustness of the local cost function. So to summarize all of this, we can see that the gradients and the frequency sensitivities tell us like what type of input features should matter and should we use, and what type of quantum circuit or quantum circuit we should make when we are trying to fit the data into a quantum machine learning model. So all of these results can be very effective in explaining the type of data that is better and the type of circuit which is more effective in certain scenarios. So this is something that we have done in the span of 6 weeks, and we think that the time was very little. If we have more time, if we had more time again, we would have more better results and a more better direction in enhancing this explainability of the quantum circuits. That's all from our side. Thank you very much. So if you have any questions, you can ask. Yeah.
I do have one question.
Yeah, sure.
In classical machine learning, it seems that whenever you get into the plateau, the inertia methods is the way to kind of push toward the minimum, right? It's kind of interesting. Kind of, what's your feeling about this? Kind of, do you think in the QA or kind of any classical slash quantum methods we can apply this as well? So can I approach or can I use the best of the classical machine learning toward the quantum? What in your mind is going to be the best approach toward this?
So it's a good question. I think so. Hybrid models are a very good approach that we have. Like the major weightlifting is done by the classical part, and some of the features or the sum of the part is done by the quantum part. Again, we all know that quantum part and the quantum circuits, we cannot make them very big. So we cannot make them learn very complex function as I have shown you that you cannot increase the depth after a certain limit because it would not be very effective. Furthermore, you would have the problem of vanishing gradient. So it could be effective in a small part, but not as a larger part. So we would have to use the hybrid model. I think so that would be more effective. So I think so I've answered your question, or did you had any other part of it?
I think you answered part of it. I really appreciate it. That was a good answer. Yeah, it's somebody can pretty much like finish PhD doing this research. So thank you for digging into this.
Yeah. So we are very thankful to Oliver because he guided us very in the initially like the basics and the paper that we actually implemented, and then we ran the results and did some variation of the results, and we came to this conclusion. So again, this is a very basic result and the work of maybe a few weeks. We are also like working on to stretch the results and do some further experimentation on actual quantum hardware and see the effects, like what is the probabilities and what are the limitations or what are the thresholds in actual hardware that can learn these functions or these data sets.
Thank you.
If anyone has any other question, we are happy to answer.
Any more question? If not, I think let's thank the speaker again. Then this is the last the live presentation of today, which is the team SQI. Dongwan Kim will present, and are you here, Dongwan?
제가 발표를 대신 해야 될 것 같습니다.
예, 알겠습니다.
화면 공유하겠습니다. 보이시나요?
네, 잘 보입니다.
네, 혹시 그 통역을 어떻게 진행하는지 좀 여쭤봐도 될까요?
지금 있는 채널에서 바로 말씀을 하시면 될 거고요. 동시
네,
통역을 여기 이제 통역사님께서 진행해 주실 계획입니다. 한국어로 발표하시나요?
네, 맞습니다.
네, 그렇게 해주십시오. 예, 시작하시면 되겠습니다.
네, 안녕하십니까. 팀 SQI에서 발표를 맡은 권주원이라고 합니다. 저는 저희 팀은 파노스 박사님과 함께 멘토링 프로그램을 진행을 하였고요. 그다음 연구 주제는 Applying Effective Dimension on Variational Quantum Eigensolver입니다. 네, 그래서 컨텐츠로는 인트로덕션을 하고 그다음 두 가지 연구 주제 저희가 진행했던 연구 주제에 대해서 소개하는 식으로 진행을 해보도록 하겠습니다. 먼저 업스트랙트가 있는데 업스트랙트 대신에 나중에 이어서 이제 설명을 더 구체적으로 하는 방식으로 해서 업스트랙트를 생략하도록 하겠습니다. 인트로덕션을 먼저 설명드리도록 하겠습니다. 먼저 이펙티브 디멘션이 무엇인지에 대해서 간략하게 설명을 드리도록 하겠습니다. 이펙티브 디멘션이라는 것은 퀀텀 머신러닝에서 모델의 표현력과 일반화 성능을 평가하는 지표로 사용되는 하나의 지표입니다. 이펙티브 디멘션은 피셔 인포메이션 매트릭스를 기반으로 계산이 됩니다. 다음으로 피셔 인포메이션 매트릭스에 대해서 간단하게 설명을 드리도록 하겠습니다. 피셔 인포메이션 매트릭스는 이펙티브 디멘션을 계산할 때 사용되는 또 다른 지표로서 파라미터 스페이스에서 각 파라미터에 대해서 얼마나 코스트 펑션이 민감한지에 대해서 평가를 하는 지표입니다. 다음으로는 VQE에 대해서 간단하게 설명을 드리도록 하겠습니다. VQE라는 것은 하이브리드 퀀텀 클래시컬 알고리즘으로서 양자계의 그라운드 스테이트 에너지를 예측해내는 모델 퀀텀 릴레이셔널 퀀텀 모델입니다. 알고리즘입니다. VQE에 대해서 구조에 대해서 간략하게 설명을 드리자면 그저 파라미터라이즈드 퀀텀 서킷 안자재라고 부르는 퀀텀 하드웨어 부분이 있고 메저먼트 아파라투스로 이제 해밀토니안을 매핑하는 파트가 있고 다음으로 클래시컬 옵티마이저로 파라미터 업데이트를 하는 파트가 있습니다. 그래서 모델이 어떻게 진행이 되는지 설명을 드리면 먼저 퀀텀 하드웨어에서 이니셜 스테이트를 예측을 트라이얼하게 퀀텀 스테이트를 준비를 하고 그다음에 메저먼트 아파라투스로 해밀토니안 매핑이 된 구조로 해밀토니안에 대한 기대값을 측정을 해냅니다. 그리고 클래시컬 옵티마이저를 활용해서 해밀토니안 기대값을 기반으로 파라미터 업데이트를 진행을 하면서 이터레이션을 계속 진행을 하게 됩니다. 그리고 VQE가 이제 중요한 이유에 대해서 말씀을 드리도록 하겠습니다. 복잡한 퀀텀 시스템에서 해밀토니안은 보통 익스플릿하게 주어지는데 이에 대한 아이겐 밸류와 아이겐 스테이트를 아날리틱하게 계산하는 것이 굉장히 어렵습니다. 따라서 버리셔널 퀀텀 아이겐 솔버로 최적화 기법을 사용해서 최적 그라운드 스테이트 에너지를 애널리틱하게 푸는 것이 아니라 최적화 기법으로 풀 수 있다는 데 의의가 있습니다. 이번 연구에서 저희는 하이드로젠 모레큘에 대한 해밀토니안을 가지고 연구를 진행하였습니다. 그리고 VQ에 대해서 몇 가지 병목들이 있는데 두 가지가 크게 있습니다. 첫 번째로는 안자체 스트럭처 디자인에 대한 부분이고 두 번째로는 파라미터 이니셜라이제이션입니다. 안자체 스트럭처에 의해서 스트럭처를 어떻게 디자인하는지에 따라서 파라미터 스페이스의 지오메트리가 달라지고 트레이너빌리티가 달라지기 때문에 안자체 스트럭처 디자인이 중요하다고 볼 수 있습니다. 또한 주어진 안자체 스트럭처에 대해서 이니셜 파라미터 포인트를 어떻게 설정할 것인지에 따라서 학습 시간이 굉장히 상이하게 달라지고 또한 학습 성공 여부도 달라지기 때문에 파라미터 이니셜라이제이션도 굉장히 중요하다고 할 수 있습니다. 그래서 이번 연구에서 저희는 안자치 스트럭처와 안자치 스트럭처 디자인과 파라미터 이니셜라이제이션 메소드를 이펙티브 디메이션을 이용하여 개발 이용해서 구현을 해봤습니다. 파라미터 이니셜라이제이션부터 먼저 설명을 드리도록 하겠습니다. 저희 전략은 다음과 같습니다. 로컬 이펙티브 디멘션을 활용하는 것인데, 로컬 이펙티브 디멘션이 많다는 것은 국소적으로 그 파라미터 포인트에 정보량이 많다는 것이므로 이것이 좋은 이니셜 파라미터 포인트가 될 수 있다라는 것이 핵심 아이디어였습니다. 그래서 어, 조금 더 세부적인 로직 플로우를 말씀드리자면 먼저 글로벌 수입을 해줍니다. 파라미터 스페이스가 있으면은 유니폼하게 파라미터 스페이스를 샘플링해서 각각의 샘플들에 대해서 로컬 이펙티브 디멘션을 계산을 해줍니다. 그리고 그 로컬 이펙티브 디멘션을 계산한 것을 가지고 샘플들 중에서 높은 로컬 이펙티브 디멘션을 가지는 샘플들을 추가로 샘플링을 선별을 해줍니다. 그래서 높은 로컬 이펙티브 디멘션을 가진 샘플들을 이용해서 그 샘플들 근방에 하이퍼큐브를 하나 생성을 해주고 하이퍼큐브에서 평균 로컬 이펙티브 디멘션을 추가로 계산을 해줘서 그 중에서 가장 평균 로컬 이펙티브 디멘션이 높은 샘플을 이니셜 파라미터 포인트로 설정하는 것이 저희의 아이디어였습니다. 그런데 거기에는 몇 가지 이슈가 있었습니다. 그 이슈는 무엇이냐면 첫 번째로 이펙티브 디멘션이 일반적으로 베리에이셔널 퀀텀 알고리즘에서는 정규화 팩터가 들어가게 됩니다. 피셔 인포메이션 매트릭스 앞에 정규화 팩터가 들어가게 됩니다. 그런데 VQ의 경우에는 인풋 샘플 데이터가 없기 때문에 정규화 팩터가 불안정해지는 그런 경우가 발생할 수 있습니다. 따라서 이러한 불안정성을 해결하기 위해서 이펙티브 디멘션을 정의를 할 때 피셔 인포메이션 매트릭스 앞에 노멀라이제이션 팩터를 없애는 방식으로 이펙티브 디멘션을 새롭게 정의를 하였습니다. 또한 피셔 인포메이션 매트릭스에서도 문제점이 있었는데요. 피셔 인포메이션 매트릭스가 일반적으로는 그 그레디언트의 아우터 프로덕트의 기대값으로 계산이 되는데 VQ의 경우에는 인풋 데이터 샘플이 없다 보니 기대값을 계산하는 게 아니라 단일 그레디언트의 아우터 프로덕트로 매트릭스가 표현되기 때문에 표현되고 이것은 결국에 매트릭스의 형태가 랭크가 1과 같다는 것을 의미하게 됩니다. 그리고 추가적으로 피셔 인포메이션 매트릭스에 노멀라이제이션을 가한 다음에 디터미넌트를 계산하게 되면은 랭크 1 매트릭스의 디터미넌트가 이제 1000의 형식으로 나오기 때문에 모든 파라미터 스페이스 포인트에서 동일한 로컬 이펙티브 디멘션을 계산을 해내는 문제점이 있었습니다. 따라서 이러한 문제점을 해결하기 위해서 피셔 인포메이션 매트릭스를 unnormalized 피셔 인포메이션 매트릭스로 사용을 해서 이펙티브 디멘션 계산에 사용을 하였습니다. 다음은 실험 결과를 말씀드리도록 하겠습니다. 먼저 실제로 로컬 이펙티브 디멘션이 좋은 이니셜 파라미터 포인트를 제공을 하는지 여부를 파악하기 위해서 테스트를 진행을 해보았습니다. 먼저 파라미터는 다음과 같이 설정을 하였습니다. 모든 파라미터 포인트를 0으로 초기화한 것부터 모든 파라미터 포인트를 2파이로 설정하는 것까지 0.1 단위로 수입을 해서 파라미터 셋을 만들고 그 파라미터 셋에 대해서 로컬 이펙티브 디멘션과 옵티마이제이션 런타임을 계산을 해보았습니다. 그래서 로컬 이펙티브 디멘션과 런타임 간의 상관관계를 분석을 해보았는데요. 음의 상관관계가 뚜렷하게 나타난 것을 볼 수 있었습니다. 따라서 로컬 이펙티브 디멘션이 어느 정도 좋은 이니셜 파라미터 포인트를 제공한다는 결론을 내릴 수 있었습니다. 또 이번에는 파라미터 셋 밸류 수입에 대해서 로컬 이펙티브 디멘션을 플롯을 해보았습니다. 그 결과 두 개의 구간에서 뚜렷하게 로컬 이펙티브 디멘션이 낮은 구간이 발생한다는 것을 알 수 있었습니다. 그리고 그 두 구간, 이 1, 2, 그리고 4, 5 구간에서 로컬 이펙티브 디멘션이 낮게 나타났는데 그 1, 2, 4, 5 구간에서 옵티마이제이션을 진행했을 경우에 런타임이 굉장히 높게 나오는 것을 발견할 수 있었고, 또한 해당 구간에서 그 옵티마이제이션 값, 그러니까 해밀토니안 기대값도 굉장히 불안정하게 나온다는 것을 알 수 있었습니다. 또 마지막으로 파라미터 셋 밸류에 대해서 이펙티브 익스펙테이션 해밀토니안에 대한 익스펙테이션 밸류를 직접 구해봤는데 아까 말씀드렸던 구간에서 굉장히 상대적으로 높은 해밀토니안 기대값이 나온다는 것을 알 수 있었습니다. 따라서 결론적으로 음, 높은 로컬 이펙티브 디멘션을 가지는 구간이 더 좋은 이니셜 포인트를 제공할 가능성이 높다는 결론을 내릴 수 있었습니다. 이러한 실험 결과를 바탕으로 실제로 로컬 이펙티브 디멘션을 활용한 파라미터 이니셜라이제이션 메소드 알고리즘을 구현해보고 실행을 해보았습니다. 조금 더 구체적으로 말씀드리자면은 알고리즘에 대해서 실질적으로 파라미터 스페이스의 디멘션이 커질수록 차원의 저주 때문에 이제 파라미터 스페이스를 유니폼하게 샘플링하는 게 좀 어려워집니다. 따라서 직접적으로 유니폼하게 파라미터 스페이스를 샘플링하기보다는 라틴 하이퍼큐브 샘플링 방식을 이용해서 어, 유니폼한 샘플링 방식을 모사를 구현을 해보았습니다. 그래서 전체적인 로직 플로우는 다음과 같습니다. 먼저 글로벌 샘플링을 LHS 메소드를 이용해서 해줍니다. 그리고 글로벌 샘플에 대해서 로컬 이펙티브 디멘션을 각각 계산을 해줍니다. 그리고 로컬 이펙티브 디멘션이 높게 측정된 샘플들에 한해서 엘리트 셋을 만들어줍니다. 또 다음으로 로컬 샘플링 어라운드 엘리트로 해서 그 엘리트 셋에 대해서 엘리트 셋 각각에 대해서 하이퍼큐브를 하나 설정을 하고 하이퍼큐브에서 또 한 번 로컬 샘플링을 해서 평균적인 로컬 이펙티브 디멘션 값을 계산을 하게 됩니다. 그리고 최종적으로 가장 평균 로컬 이펙티브 디멘션이 높은 샘플을 고르고 그 샘플 안에서도 가장 로컬 이펙티브 디멘션이 높았던 샘플을 하나 설정을 해서 그것을 이니셜 파라미터 포인트로 설정을 하는 식으로 알고리즘을 구현을 해보았습니다. 그런데 해당 알고리즘을 직접 실제로 실행해 본 결과가 그렇게 좋진 않다는 것을 확인할 수 있었습니다. 먼저 프리퍼레이션 타임도 굉장히 길었고, 그다음에 옵티마이즈드 에너지도 이상적이지 않게 나왔고, 그다음에 런타임도 굉장히 길게 나왔습니다. 이러한 그 이렇게 불안정하게 알고리즘이 작동하는 원인을 분석해 본 결과 하이퍼 파라미터가 굉장히 중요하게 영향을 미친다는 것을 알 수 있었습니다. 예를 들어서 하이퍼 큐브를 어느 정도의 크기로 잡을지에 대한 하이퍼 파라미터도 설정할 수 있었는데 이 하이퍼 파라미터를 어떻게 적절하게 설정하는지에 따라서 모델의 성능이 굉장히 많이 좌우된다는 것을 확인할 수 있었습니다. 그래서 이 저희가 고안해낸 아이디어의 한계점으로는 어, 높은 차원의 파라미터 스페이스에 대해서 LHS 메소드를 활용을 한다 하더라도 유니폼하고 어, 전역적으로 샘플링을 하기가 어렵다는 차원의 저주를 극복하지 못했다는 문제점이 있었고 또 로컬 박스 사이즈를 어떻게 설정하는지에 따라서 모델이 굉장히 민감하게 반응을 하기 때문에 이 로컬 박스 사이즈를 어떻게 최적화할 수 있는지에 대해서도 추가적으로 연구를 해야 될 것 같다고 생각을 했습니다. 다음으로는 이펙티브 디멘션 베이스드 안자체 디자인입니다. VQ에서는 안자체 스트럭처 디자인이 파라미터 스페이스의 지오메트리에 영향을 많이 주기 때문에 중요합니다. 그리고 하드웨어 이피션트 안자체를 디자인하면서 표현력을 함께 올리는 그런 구조를 설계하는 것이 굉장히 중요합니다. 그런데 이번에 저희 연구에서는 모델의 익스프레시비티를 높이는 방향으로 이펙티브 디멘션을 활용해서 안자체 디자인하는데 연구를 해보았습니다. 그래서 이펙티브 디멘션이 모델의 익스프레시비티를 정량적으로 하는 지표로 사용된다면 그것이 안자체 스트럭처 디자인에도 사용이 될 수 있지 않을까라는 아이디어로 알고리즘을 구현을 해보았습니다. 로직 플로우는 다음과 같습니다. 먼저 새로 주어진 안자치 게이트에서 시작을 해서 트라이얼하게 안자치를 추가를 해봅니다. 그리고 그 추가된 안자치 스트럭처에 대해서 이펙티브 디멘션을 계산을 해보고 그 이펙티브 디멘션이 증가했으면은 그 안자체 스트럭처를 채택을 하고 증가하지 않았다면은 안자체 스트럭처를 기각하는 방식으로 이터레이션을 돌리면서 알고리즘이 작동하도록 구현을 해보았습니다. 그래서 코드를 조금 더 구체적으로 설명을 드리자면 먼저 게이트 캔디데이트 풀을 컨스트럭트 해줍니다. 그래서 저희가 이번에 연구에서 사용했던 게이트로는 RY 게이트와 Controlled RY 게이트가 있습니다. 그래서 Controlled RY와 RY 게이트를 이용해서 게이트 풀을 만들어주고 그 다음에 안잣지 업데이트를 해줍니다. 게이트 풀에 있는 게이트 중에서 랜덤하게 게이트를 골라서 그 게이트를 기존 안잣지에 추가를 해줍니다. 그리고 추가된 업데이트된 안자체 스트럭처에 대해서 이펙티브 디멘션을 계산을 해줍니다. 그리고 이펙티브 디멘션 기반으로 안자체 업데이트를 해줍니다. 그래서 이펙티브 디멘션이 증가했으면은 그 안자체 스트럭처를 채택을 하고 그렇지 않으면 기각하는 방식으로 이터레이션을 돌려줬습니다. 그래서 이터레이션을 돌린 결과는 다음과 같습니다. 이 왼쪽의 그래프를 보시면은 이터레이션 횟수가 올라가면 올라갈수록 이펙티브 디멘션이 증가한다는 것을 확인할 수 있었고 이터레이션 오른쪽에서 보시는 것과 같이 이터레이션 횟수가 증가함에 따라서 안자츠의 복잡도 또한 그러니까 안자츠 레이어의 복잡도가 증가한다는 것을 확인할 수 있었습니다. 그리고 여러 가지 해밀토니안과 베이시스와 여러 가지 해밀토니안에 대해서 실제로 알고리즘을 실행을 해보았습니다. 그 결과 이터레이션 수가 증가하면 증가할수록 이제 그라운드 스테이트 에너지가 점점 감소한다는 것을 확인할 수 있었습니다. 이를 통해서 이펙티브 디멘션 기반으로 안자체 스트럭처를 안자체 스트럭처 디자인을 하는 것이 실제로 모델의 성능에 도움을 준다는 것을 확인할 수 있었습니다. 네, 이상입니다.
네, 마지막
질문
발표까지
있으시면
잘
네.
들었습니다. 혹시 질문 있으시면 해주시면 좋겠고요. 영문으로 해주셔도 아마 번역이 가능할 것 같습니다. 통역이 가능할 것 같습니다. If you have a question in English, I can translate it for you. So, any questions from audience? Yeah, so I think that's it for today's presentations. There was like the five teams, five teams like the attended this like the mentoring program, and four teams present today, and the one team was not able to present today, so they sent us their like recorded video, which will be uploaded on YouTube along with the recorded like presentation today. So I like to thank every mentors who mentored this like the all the like the mentees throughout this program, and also all the applicants and all the attendees for this mentoring program. I really appreciate your hard work and the interesting works related to these like various topics. So that's it. That's it for today, and I'd like to thank everyone who attended today. Thank you. Thank you a lot.
Yeah, thank you, Professor Kim, and thank you everyone for presenting. This was incredible, really well done. And Danny, Dr. Dahl, thank you for the help that you provided here. Well done.
It's my
Thank
pleasure.
you. Thank you, everyone.
Today, I will be sharing our project titled IonQ Adaptive Hybrid Embedding, carried out by our team IQ. The focus of this project is to explore how different quantum data encoding strategies behave when tested on IonQ's trapped ion hardware. Despite the hardness of implementing in real quantum hardware, our experiment was in simulator, but the starting point was doing the same thing in IonQ's hardware. In this talk, I'll walk you through the motivation behind our study, the IonQ hardware characteristics, the encoding methods we implemented, and then I'll show you the experimental results with a discussion of insights and next steps. In quantum machine learning, before any training or optimization, we face a very crucial question. How do we actually put classical data onto a quantum computer? This process, which we call quantum data encoding or embedding, essentially defines how expressive the quantum model can be and how resource demanding it will become. There are several popular methods: angle encoding, data re-uploading, amplitude encoding, hybrid approaches, and kernel-based embeddings. Each comes with trade-offs. Angle encoding is simple and hardware efficient, but not very expressive. Amplitude encoding is powerful, but circuits become deep and hard to execute. To properly design our experiments, it was important to understand IonQ hardware landscape. IonQ provides three main targets. First, there is a simulator, which supports up to 29 qubits. It uses the same gate set as the actual hardware, so it's a great environment to validate our circuits before we spend real quantum resources. Next, the area QPU. This is a 25 qubit trapped on processor with built-in biasing and commercial grade fidelity. And finally, Forte, which is currently in preview. In our study, we implement and compare 6 encoding methods: angle encoding, data re-uploading, or DR, amplitude encoding, hybrid encoding, quantum kitchen sinks, kernel feature maps. All 6 methods were implemented as separate classifier modules in our codebase. Importantly, we trained them under a PyTorch-based loop. This way, we ensure fairness in comparison, same optimizer, same loss function, same batch size, and learning rate schedules. Our evaluation pipeline starts from pre-processing the dataset, applies PCA to reduce dimensionality, encodes the data into quantum circuits according to each method, runs training on either a simulator or IonQ hardware, and finally logs metrics such as accuracy, F1 score, circuit depth, and gate counts. This standardized pipeline allowed us to isolate the effect of encoding itself without confounding variables from the training process. Let's start with angle encoding, the most straightforward method. Here, each classical feature is directly mapped to a rotation around y-axis of the qubit. So if we have d features, we use d qubits to apply ry rotations with angles proportional to the input values. To add some correlation between qubits, we insert a linear chain of CMOS. On top of that, we apply variational layers consisting ry and rz on every qubit, followed again by optional entanglement. At the end, we measure the expectation value of the z operator on the last qubit and use that as our classification logic. Angle encoding is shallow and hardware efficient, making it natural baseline for our experiments, especially in low-dimensional PCA settings like 16 features. Next is data re-uploading. This method extends angle encoding by injecting the same data features multiple times across different layers of the circuit. Each layer follows this structure. First, we apply R-by rotation with the data, then additional R-by rotation with trainable parameters, and finally a chain of CMOS for entanglement. By repeating this pattern 8 times, we allow the circuit to build up nonlinear decision boundaries, even though each individual layer remains simple. The key trade-off is between expressivity and noise. With more layers, the model becomes more expressive, and indeed, this method is proven to be universal in limit of many layers. But of course, as depth increases, the circuit becomes more vulnerable to noise. For our implementation, we initialize weights uniformly on 0 to 2 pi to ensure wide range of parameter space. And again, use the Z expectation of the last qubit for classification. DRU is therefore more expressive extension of angle encoding at the cost of additional parameters and depth. Amplitude encoding takes a very different approach. Instead of mapping features to rotational angles, it embeds the entire normalized vector directly into amplitudes in a quantum state. In our implementation, it creates two variants. The exact version uses Miltonian state preparation to precisely map a length to vectors onto the amplitudes of n qubits. This works well for small dimensions like PCA32. The approximate version is designed for higher dimensions like PCA64. After encoding, we add shallow variational RY and RZ layers and optional entanglement to allow the circuit to adapt. We also validate inputs by padding or truncating them into dimensions. Hybrid encoding is our attempt to combine the strengths of angle and amplitude encoding. Here's how it works. We split the features into two groups. The first K features are encoded using angle encoding, and the remaining features are encoded using amplitude encoding. We then connect these two blocks with boundary CMOS, ensuring cross-entanglement between the angle and amplitude parts. On top of this, we apply variational layers with Rx, Ry, and Rz rotations, together with entanglement strategies such as linear, circular, or even flow connectivity. Kernel feature map provides a different perspective. Instead of optimizing parameters, we use fixed quantum feature maps and compute kernel metrics that can be fed into classical methods like SVMs. We implemented two common maps, the ZZ feature map and IQP feature map. To bridge the classifier, we also created a variant with lightweight variational heads on top of the feature maps. For analysis, we computed kernel metrics pairwise. These metrics essentially measure the similarity between quantum states produced by different inputs. With these, we can use classical kernel methods to perform classification. Quantum kitchen sinks use randomness to create expressive quantum embeddings. We start by generating random parameters for Rx, Ry, and Rz rotations, as well as for entanglement gates. Input features are then embedded through random linear combinations mapped to these rotations. On top of that, we add a small variational head with Ry and Rz layers. Importantly, QKS does not require gradient-based optimization of random layers. They are fixed once chosen. Instead, we can average over multiple random seeds, an approach called ensemble QKS to improve robustness. So let's move to our experiment part. Due to limitations, our training script, which currently only supports binary classification, we restrict our experiment to T2 binary test. We used FashionMNIST dataset reduced to 16 dimension using PCA. The training parameters were kept consistent, 5 epochs, batch of 64, and 1 layer. We test 3 encodings under these settings: QKS, kernel feature maps, and amplitude approximate. The results reveal interesting difference between the methods. QKS achieved the highest accuracy, around 52%. This suggests that random nonlinear embeddings can indeed capture decision boundaries effectively. KFM achieved the highest F1 score, about 67%. While this accuracy was slightly lower, the balanced F1 indicates it handled class distribution more robustly. Amplitude approximate showed lower accuracy overall, and its F1 was in middle range, meaning it was not entirely ineffective, just less consistent. Looking at the training curves gives us further insight. For QKS, accuracy improved steadily but plateaued early, suggesting it quickly captures the low-hanging patterns but then stops improving. KFM, on the other hand, started more slowly but maintained a very stable F1 across epochs, showing robustness. Amplitude approximates show more fluctuations, which is a sign of sensitivity to initialization and perhaps insufficient expressivity at low depth. These results highlight a trade-off between convergence speed, stability, and final performance. QKS is fast and accurate, KFM is stable and balanced, and amplitude approximate is lightweight but less competitive. Thanks for listening.